Celentano, Chen Cheng, and Ashwin Pananjady. So just to fix the ideas, we'll talk about things that are a bit more general than this, but just to fix the ideas, consider a function f, which is from Rn to R. And suppose that you're interested in minimizing over some parameter theta the composite function, which is just f applied to x theta, where here x is just some matrix in R n by b. This x throughout will be our data matrix. Later we will put an assumption that it is random, but for now we don't have to think about that. This specific class of composite optimization problems already encompasses some fairly interesting examples. For instance, one of them is a maximum likelihood estimation for a generalized linear model. So for instance, if I have a set of observations yi that take some potentially nonlinear function phi, apply it to the inner product between your data xi and some unknown parameter star, which is then corrupted by some additive noise with variance sigma squared. If we assume that this noise is Gaussian distributed, then the maximum likelihood function associated to this gives us the loss function So this simple loss already captures several interesting problems. For instance, mixtures of linear regression, phase retrieval, amongst many others, where the only distinction that you need to make to specify each of these problems is specifying this link function. The important thing that I want to point out here is that even this simple class of nonlinear least squares problem, you can run into some difficulties. For instance, in both of these problems, this is a non-convex loss. And in the at least non-smooth variant of phase retrieval, this is a non-convex and non-smooth loss. Now, more to the point, you may know that non-convexity isn't necessarily a barrier to doing anything. But for instance, in the mixtures of linear regression problem, even deciding whether or not the data, so yi, deciding whether or not there exists a solution to the mixtures of linear regression problem for that data is an NP-hard problem if the data is allowed to be worst case. So in general, for problems of this type, in order to try and say anything, you have to make some assumptions on the data. Okay. Otherwise, you have no computationally efficient hope of doing
the mixture of linear model.
Mixture of linear model means I take here, I fix, let's say, theta star 1, theta star 2, with probability 1/2 or some weight. I get it from linear model with theta star 1, probability whether I get it from the other. In the case where they're kind of antipodal, so I have theta star and negative theta star, and if I have no noise, this is the same problem for space retrieval. Okay. So because of this, we need to make some assumptions. So for us, the running assumption is going to be that of random design. And we're going to make, I will be intentionally simple about this. I'm not going to pretend that this is a very general assumption. I just want to try and understand something about these algorithms. So the assumption I'm going to make is very strong. I'll assume that the data xij is IID standard Gaussian. Well, actually, I'll put the variance 1 over d just for normalization, but whatever you pick for this variance, it's okay. You can normalize it at a different time. This just ends up being convenient for us. So this is going to be our running random data. Now, what we're interested in is we'll be interested in the dynamics of iterative algorithms. Why is that? This is because downstream, the types of questions that we'll be trying to answer are both statistical and computational. So on the statistical side, if say theta hat is a minimizer of this, how good is theta hat minus theta star? Okay, so how close is this this empirical risk minimizer, how close is it actually to this ground truth? The second thing is, since these problems are often non-convex, can you actually reach theta hat? And the second thing is, which method should we use to actually reach theta hat? So just to sketch why this might be non-trivial in some sense, if this is the loss function we're trying to minimize, it could be the case that whatever algorithm we use converges to this local minimum. We could have another algorithm that converges to this guy. We could have another one that converges to this. And we want to understand for these three algorithms, I mean, are they converging to relatively similar properties? Or are they converging to different things? Since we don't have any global structure, we don't have convexity or strong convexity or anything like that to guide us, a priori, we're not sure which of these bins we fall into. So the way in which we can try and understand both of these questions at the same time is through the dynamics of the algorithm. So in particular, what I mean by dynamics is I want to produce a plot like this. This is a completely deterministic plot. So no data is ever going to be used to draw this. Or on the x-axis, I have iterations. And on the y-axis, I have my error. Where error, I mean here, theta t, or I'll say k, minus theta star. Okay? So on the y-axis, I'm plotting my statistical error. There's another function error. On the x-axis, I'm going to see after each step of the algorithm. Now here, I could have one algorithm that, let's say, converges like this, and then tails off. So if I've computed the dynamics of this algorithm, maybe it tails off, it converges to this point. I could have another algorithm which converges very fast, let's say this, and not only does it converge very fast, it converges to a much lower error, okay? And if I have my hands on the dynamics of the algorithm, I'll be able to ascertain, okay, a priori, this is the algorithm that I should choose, okay? So this is the kind of thing we're going to be after today. But from this point on in the talk, all I'm going to try and do is derive expressions for these and derive techniques for how you can derive these kinds of plots. Yeah.
I mean, assuming though, like in practice, unless you simulate your own data, you don't know theta star. So like
You don't necessarily
really see this graph in practice.
You don't need to know theta star for that. So it only matters so these curves are only functions. So let's say this point here, this is only a function of the iteration k. Let's say the noise level sigma, the algorithm that you use, and the size of theta star. So in particular, what you can do, this, you're right, you don't know. This is easier to estimate quantity though than theta star. So this is a one-dimensional quantity. Theta star is a d-dimensional quantity. So this you should expect to estimate much easier.
Okay.
You also don't know sigma.
Right.
You won't know that in practice. But these curves you can generate for any, you can pick a conservative curve. So you can generate these curves for some large swath of sigma. You can generate these curves for some large swath of theta stars and see, yeah.
Nice.
But these you generate, you can do it completely offline. So I can give you an example, like for a particular algorithm we've done this for, we literally ran, I think we did a hyperparameter search on these deterministic curves for over 10,000 hyperparameters, and it takes like 5 seconds to run. So these are just like easy functions. For specific algorithms, these can be very easy functions to compute, numerically at least.
I see.
Okay. Yeah.
Why doesn't it depend on the randomness in the xi? Sorry.
The randomness in the x, so whatever this point, so the type of guarantee that we're going to show is that this thing converges to this. So this convergence is
Right, a limited n.
Yeah, exactly. Okay, so what are the types of algorithms that we're going to consider? There's two types. The first is a generalized first order method. What do these algorithms look like? they're specified by two sequences of Lipschitz functions. So fu indexed by k is the iterate. This is a function from Rn to Rn. Fv is a function from Rd to Rd. And our iterates look like the following. I'll update uk plus 1. This is equal to fu at time k plus 1 applied to x on vk, and perhaps with some dependence on the past. Here, vk plus 1, we update as fv update by the negative x transpose uk. And again, you can have some dependence on these. Okay, so just to show you an example of this, you can embed the gradient descent dynamics in this general first order method. So gradient descent, this iterates the following. I take theta k plus 1, this is equal to theta k minus some step size, let's say eta k, gradient x transpose, gradient of x theta k. So this is just, I'm doing gradient descent on this general composite optimization problem. How do I embed it as a first order method? I can do the following. I can just increase the iteration. I can blow it up by 2. So what do? I take u2l plus 1. Here, this is going to be the gradient of x applied to v2l. I take v2l plus 1. This is exactly just going to be v2l. So at time 2l plus 1, I update u2l plus 1 to just be the gradient, and I keep v2l plus 1 to just be constant. On the other hand, at time 2l plus 2, I keep u2l plus 2 constant. And then I update v according to this. So this is going to be v2l plus 1 minus theta l u x transpose u2l. Okay. So these generalized first order method dynamics, they simulate these gradient descent dynamics. If I just take v2l plus 1, v2l plus 2, this is going to correspond to theta l plus 1.
What are these operator definition? The function, these two?
These ones, this is just a function. Here, the u is just indicate, it's just indicating that this is going to
Updates
apply.
on U space, right?
Yeah, exactly. And then these are a sequence of functions that are indexed by k.
Yeah, what's the definition corresponding to this gradient descent?
Yeah, so for this one, it's overloaded a little bit. This guy here, this is going to be my fk plus 1 u. Just the gradient of f. So if f is, for instance, a smooth function, this is going to be a Lipschitz function. So this is fine. And here, f is just the identity. Because I'm just applying some function f here to negative x transpose k. So not the identity, maybe the identity map scaled by this eta and this constant.
What is the intuition? Why do the U and V joint space instead of just the prime space, the variable theta?
There's no, it's just that this captures a slightly larger set of algorithms. So for instance, approximate message, the reason this generalized first order method class is defined in this way is it's coming from the approximate message passing literature. Approximate message passing is most easily written in this way. And the original proof to track the dynamics of, say, gradient methods is by reduction to approximate message passing. So I only state this in the sense that these types of algorithms, we know in principle how to track the dynamics by a reduction to approximate message passing. The techniques I'll talk about today generalize those. So we will recover and strengthen those guarantees. But this is not going to be the class of interest for us. This is a class that there exists dynamics for, and which subsumes common algorithms like gradient descent.
The mirror descent can be also formulated in this way.
Mirror descent can. Mirror descent, accelerated notions of gradient descent also.
You work on the U space, right? So I sort of this U and V, perhaps one corresponds to the updates in the due space, and the other one, you just map it back, right?
I think if you were to write mirror descent, you would do it like that.
Sorry, I was late. So what's the connection between UV and the parameter theta?
Yeah, so here you're just blowing up the iterations by 2. So for every iteration, you blow it up by 2. And what you'll do, let's say to recover theta k plus 1, that's just V at iteration 2k plus 2. So here, the only reason you blow it up is so that you can, at the odd iterations, you're just taking these gradients. And then at even iterations, you're updating your parameter. So you can think of every even iteration of V, that's your parameter for theta. In fact, because you never update V at an odd iteration, you can just pick either the even or odd one, but that'll be your parameter.
And in the original story, when I was reading this,
Yeah.
where does U and V come to play? It's
In this story, we're just interested in theta.
Uh-huh.
So here, this is just the class, this is just the general class of algorithms from which it captures that, if you run gradient descent.
Okay.
So I only state that this is the usual definition, at least in the approximate message passing literature. I'm saying only that it's sufficient to cover these kinds.
But on the top, you have FU, FV, but in the example, it's just an F, so.
Yeah, I'm overloading notation a little bit. This F corresponds to the F on the first board. These FU and FVs, these are just update functions. So in this one, FU is just the gradient of F, of that guy. And in this one, FV is this constant offset minus the constant eta L times thing. Okay. Yeah. Now, these are not the only kinds of, these are not useless book, right? So these are not the only kinds of algorithms that we might be interested in. I'm just going to erase this out. So, for instance, we might be interested in something like a proximal point update. So proximal point will update the following. I'll take theta k plus 1. Minimizer of my original function f and theta plus some penalty. Okay, so for instance, if my original function f is poorly conditioned, each iteration here solves a better conditioned version of the original problem. And this will eventually converge, let's say if f is convex, to the actual minimizer. Now, in order to solve algorithms like this, the second class of algorithms that we'll consider is what are called saddle updates. Actually, before I even say it, more generally speaking, how most iterative algorithms that I know of tend to be defined are kind of in a way like this. Indeed, gradient descent is also defined in this way. You have your starting iterate theta k. You make some local convex approximation around theta k. It doesn't matter that the global function is non-convex. Your iteration is just going to minimize this local surrogate. That gives you this point here. Now you have theta k plus 1. And you do the same thing. Minimize it here. You have theta k plus 2. So gradient descent indeed iterates in this way. It makes a local quadratic approximation, minimizes it. This proximal point update is doing the same thing. It's making a local strongly convex approximation around it, minimizing it. And the general class of algorithms that we'll consider here is what we call saddle point. So again, here I'm going to blow up to 2 variables. And these 2 variables are going to be the saddle. So U is in Rn, V is in Rd of this quantity. U transpose XV plus some penalty function PV can be indexed by K, V minus some penalty function, du, x plus k of u. And I'll assume here pku, pkv are strongly convex. Okay, so this class of updates saddle updates captures the proximal point method. How does it capture proximal point? For proximal point, we can simply take, if say f is convex, we can just take the convex dual. Okay, so for proximal point, we can rewrite these iterations as uk plus 1 vk plus 1. This is the saddle of u transpose xv plus eta k beta minus v minus vk, and then subtract off f star, where f star is the convex conjugate. So for instance, if f is strongly convex and smooth, f star is also strongly convex and smooth. So this is the simplest instance of this, but several other algorithms are also contained here. For instance, the alternating minimization updates for phase retrieval and mixtures of linear regression, the expectation maximization updates as well, just for mixtures of linear regression, and variants of this called prox-linear methods are also contained in this class. Yeah.
Is it clear that there exists unique saddle point?
Good question. Under this definition, as long as phi and phi ku and phi kv are strongly convex, yes, there is a unique saddle point. For the reduction to proximal point, you need f to be strongly convex and smooth. Actually, you need it to be smooth. You don't need it to be strongly convex. At least for the theorems that I'll state, I'll work in this general formulation. So I'll work just with penalty functions phi ku and phi kv that are both strongly convex. So there will be a unique saddle point. How much time do I have? Good. Okay, so I basically want to spend the rest of the talk deriving, or at least showing how to derive the dynamics for this kind of update. I'm not going to show how to derive the dynamics for this kind of update because it's quite a bit simpler, and the ideas I think are not quite as nice. So most of the new ideas here are for these updates. So for the remainder of the talk, I'm going to focus on this. If there's no other questions. Okay. Let me go here. So the key challenge here is actually that as I iterate, x becomes strongly correlated with all of the previous iterates. So even at iteration 2, there's some dependence between x and iteration uk and the u1 and v1. And as I go forward, there's some non-trivial correlation with all of the iterates in the paths in general. So really the key issue to try and describe the dynamics of that is that correlation with the past. And we spent quite a bit of time trying to figure out how to do the dynamics. That is primarily where we got stuck. We realized when we were writing the proof, though, that if you prove the first step where you don't have any of this correlation to worry about, if you prove this in the right way, this makes the later proof much easier and it elucidates much of the structure. So I'm going to warm up with the first iterate. And in this warm-up, I'm going to give you basically the proof technique that works for the rest of the iterates. So what do? You take your original saddle update. I mean, the schematic of the proof is the following. We take the saddle update. We then try to analyze the saddle update using what's called the CGMT, which I will say explicitly what this is. This is going to give us an auxiliary update. Now, this is a random quantity. This is also going to be a random quantity, but it lives on a different probability space. This is a priori not any easier to understand than this one. However, we're going to pass now to a Hilbert space lifting of this. So these are now going to be deterministic. And here we're going to have a deterministic equivalent of this auxiliary update. Now, even though this saddle update, like you asked, this has a unique solution, and it's actually a convex minimization, concave maximization problem. So it's quite easy to understand. Once we apply the CGMT and look at this auxiliary update that I'll write down, this has no reason to be a convex concave problem. So in principle, we made our life harder. In order to get around that, we're going to construct approximate stationary points to this. Where are these approximate stationary points going to come from? They're going to come from exactly an explicit construction of the stationary points of this deterministic equivalent. And to tie things back, we're going to plug these stationary points in here, use these to construct the approximate stationary point, and that'll help us understand the saddle. So this is the roadmap of the proof that we're going to go through. We'll be now explicit about it. So the first step is the CGMT. So what does the CGMT look like? Well, I defined two random variables. So the first random variable I define, this is P of X. So this is a function of this random matrix X. It's just going to be defined as the value of that saddle problem. So it'll be the minimum of V in Rd, max of U in Rn, U transpose XV plus V of V. I'm going to drop the K indices and the U indices just for brevity. The second random variable, A of gamma n, gamma d. Here, gamma n, this is going to be Gaussian in n dimensions. Gamma d is Gaussian in e dimensions. And this is another value of a min-max problem. Which is nearly identical to this first one. The only difference that we take is that instead of having this U transpose XV, we have a normalization by 1 over root D, norm of U times the inner product of gamma D and V. We add on this guy, and then we have the same thing. Okay, so the auxiliary problem is almost the same thing as this primary problem. The only difference is that this U transpose XV was replaced. So here you can think of, I have n by d Gaussian random variables. In this problem, I now only have n plus d Gaussian random variables. And I've replaced this, this quadratic form with this two simpler inner product of Gaussian random variables. Now, one thing to point out, I said earlier that this is a convex concave problem. This has no reason to be. And if we look at this, the reason this has no reason to be is because we don't know anything about the sign of gamma d transpose V, and we don't know anything about the sign of gamma n transpose U. So this a priori has no reason to be convex concave. But a priori also it has no reason to have a solution or a unique solution. CGMT asserts that with high probability, basically these two values coincide. So roughly speaking, the CGMT is that P of X is nearly the same as A of gamma n, gamma d. In what sense are these nearly the same? It's bounds on the CDF and the complements of the CDF. So in particular, we know that the probability for any t that P of X is greater than or equal to t, this is less than or equal to twice the probability that A of gamma n, gamma d is less than or equal to 2. And similarly for the other tail, the probability that the P of X is less than or equal to t is less than or equal to twice the probability that A of gamma n, gamma d is less than or equal to t. So the utility of this is that if A of gamma n, gamma d, if this concentrates around some value, this fudge factor of 2 doesn't matter. This is going to concentrate around some value. You have the same behavior on both tails. So in fact, this primary problem, P of X, is going to concentrate around the same value. So at least for the value of these optimization problems, it suffices just to study this auxiliary. Okay. One other thing to point out is that what we're actually interested in is we're interested in not the value, we're actually interested in the saddle itself, UK plus 1, BK plus 1. Here, this theorem is only telling us something about the value of the problem. So at some point, this is not going to be enough. We're going to have to make some argument to pass to the what these actual saddle points are. We'll do that towards the end.
So for the standard CG, I mean, I know about the Gordon's inequality.
Yeah.
So they don't, for Gordon, you don't have the auxiliary function.
You don't have these things.
Yes.
Yeah.
And the standard one I know about, you don't have this U and V index in those V function.
For the standard one, yeah. I mean, you can state it actually, the standard one is more general than this. So the standard one you state for U transpose XV, and here you just have some function Q of UV. This Q function, in order for both sides of this to hold, needs to be concave in U and convex in V, and it needs to be continuous. And then you get the same guarantee. So for us, this is a specialization of it to this setting.
Which is the paper? Who is the author for this general CGMT?
No, this one is a special case of that. So
Okay.
this is just a strict this is just a corollary of that. So or you mean the Q of UV
Yeah,
one?
Q or U one.
You can find it in, okay, so there are a couple places it's stated. The first place I think I saw it was in the 2015 paper by Christos Trampolidis,
Okay.
Samedoimak, and
Yeah, that's
the like
why.
standard one. But yeah, it's in a couple of, Andrea Montanari and Leo Melane also have a proof of it. But that's the usual formulation. Okay, so we've passed here to some auxiliary update. This is the auxiliary update that we're going to look at. I'm going to go to the other board. The next thing that we have to do is we're going to try and understand this auxiliary update. As I said, one issue with this auxiliary update is it has no reason to be convex concave. So it has no reason for us to expect there to be some nice unique min-max solution. Step 2 is to introduce a deterministic equivalent. So what is this deterministic equivalent going to look like? I want to make a loss function that looks almost exactly like this. So actually, just to make my life simpler, I'm going to define this inner function as calligraphic L of UV. I'm going to define this auxiliary inside function as capital L UV. And now I'm going to define a deterministic function, L star. L star, however, is not going to be from RD to R, from RD cross Rn to R. this is going to lie into the Hilbert space. L2 of Rn, cell sigma algebra of Rn. Gaussian measure by L2 of the same thing in dimension D. So going forward, I'm not going to mention probability space. This is just going to be the L2 space with respect to the Gaussian measure. How do we define this L star? So L star of UV, this is going to be exactly that, but now in Hilbert space. So I'm still going to have -1 over root D. So that copies over. But now instead of the norm of U, I have the L2 norm of U. And now instead of the inner product of gamma D and D, I have the L2 inner product of gamma D and D. I add to the same thing. Two, and now I have my penalties, which are not the expectation. Okay. And now again, this is now a lifted version of this. This lives in Hilbert space, but this also has, yeah.
Two questions.
Yeah.
First, so this constant factor 2 is universal.
Yeah, it's universal. Yeah.
Very sharp. You won't have a sense. Or you don't make.
Usually those events are like sub-exponentially small.
Yeah,
so
you're
you
not
don't care
gonna-
about the two.
You don't care about the two in general, like these, yeah, exactly as EJ says. These are, what we're going to see is there are going to be like sub-Gaussian type tail bounds. But you can still ask if this constant is sharp. I don't know if the two is sharp. It's a good question. I've never thought about it.
So the second question is, I guess you are implying that A is easier to compute than P, is that right?
Yeah, it will end up being easier to compute than
Why? Because right now it looks like that's a linear.
So okay, they have different properties. This is easier from the sense that like, if I were to try and run an algorithm on it, this is going to be easier. And when we actually run algorithms, this is the one that we run. A is easier just to analyze. So only for determining these precise dynamics, A is going to be easier. But the global structure of P is much nicer. This is convex concave, it's smooth, strongly convex actually. So this is super nice to analyze. Those will help us in deriving algorithm or in using this algorithmically, but they don't help us in deriving sharp trajectories.
For the estimate.
Yeah, exactly. So this is much easier for deriving the estimate. This is a good question. Okay. So this L star inherits the same problems. It's deterministic, but it still inherits the same problems as that A. Nonetheless, what we'll define is a restriction of this. So we'll look at, say I can define this thing, I'll call OPT. This is going to be the minimum over V in L2 such that the inner product of V and gamma D positive, the max of U in L2 such that the inner product of U and gamma N L2 is not negative. And this is going to be over the deterministic objective L star UV. Now, the importance of this is the following fact. Maybe I shouldn't call this OPT. Let me call the problem stop. So the fact is the following. Star admits a unique saddle point, which is U, I'll call SE, VSE. This SE quantity is going to correspond to state evolution. So it admits a unique saddle point. Moreover, this saddle point satisfies a fixed point equation. So there exist constants C1, C2, C3, C4, such that L2 inner product of USE and C1 times USC. This is equal to 1 over root D times C3 gamma D DSE L2. L2 norm squared of USE is equal to the L2 norm of C3 over root D gamma D, which is just C3 squared. The inner product of VSE with some constant C2. This is equal to fellow 4 n USE L2. And the last is that VSE L2 squared is equal to C4 over P gamma n root n gamma n L2 squared, just C4 squared. I have one quantity in here, lambda, which I haven't defined. Lambda is just shorthand for the ratio of n over d. So it's just a bit easier to stick it in there. And this concludes the fact. Okay, what is this seemingly strange looking fact? And why is it helpful? The first thing is that now this first point is fairly obvious. So this first point here is this problem here. I've now restricted the minimization over V to only the orthant where the inner product with gamma D is non-negative. So that means that this part here, this is just going to be positive. So that means that this doesn't introduce any non-concavity. Same thing here, I'm restricting this maximization over this thing to the case where this is positive, which now makes this term convex in V. Okay, so the original potential non-concavity, non-convexity, that disappears once I make these restrictions. Now, in the proof of the fact, which we won't show today, it turns out that the KKT condition of this star problem in this Hilbert space, by some miracle, this actually coincides with the KKT condition of this unconstrained problem. So this restriction doesn't really do it. Yeah.
I get confused about the randomness. So UV are random? Or?
This is completely deterministic. UV they're random vectors in L2, but this L star quantity, this is a deterministic function. So everywhere I see U, it's just the L2 norm of U, or everywhere I see V, it's going to be the L2 inner product.
So the phi V, phi U are random?
The phi V, because V is random.
Yes.
So V is random, that is still random, yeah?
Yeah.
I get confused. So the L star is, the UV in L star is random or not?
Yeah, these are random vectors.
They are random.
These are random vectors, but the L star quantity is deterministic.
Okay, so then when you say L2, that's under expectation. It's
Yeah, exactly.
not a
So,
vector, it's the expectation.
exactly, yeah. Yeah, exactly. Just to be clear, this what you're saying, this inner product is the expectation of the inner product. Okay, so first point is that because I've made this restriction,
Sorry, I have a question. UV, are they Gaussian random vector or the law is not?
the law doesn't have to be.
You don't
Gaussian.
you don't know
Yeah,
the law.
I don't know the law.
Okay.
I don't know anything about it. I've just defined it. Like they're in L2, that's all I know. And then I define a variational problem. Yes. So this first part is
Settle point is the same for the constraint. The non-constraint means that the settle point has to be within the constrained space.
Yeah.
And
But the reason why it's easy to, it makes sense to, you have to define that is because for the random problem that we're going to compare it to, it has no reason for that to be true. So there's some small fluctuations. Basically what ends up happening is that these exactly what you're saying, like these inequalities, they're never really straight. But they can be very close to zero. And here, even if you have things concentrating, they can be very close to zero and they can slip just below zero, but they're very small. So that means that this problem can still be non-convex, non-concave, but the deterministic one isn't really. Effectively, it's not. And that's only at the solution. So the better way to say it is that this problem has some unique solution, USE, VSE. If I look at the gradient of this in USE, VSE, it's going to be 0. And so that USE, VSE, that's a stationary point of this. But that a priori is not globally convex. The second part of this comes exactly from analyzing those stationary points. So if I look at the KKT condition of this, I can massage them, and the KKT condition simplifies to this system of equations. The system of equations may not look simple, but this system of equations, for anyone who has seen like the asymptotics of M estimators or anything like that, this exactly recovers all of those exact asymptotics. So these quantities C1, C2, C3, C4, by some change of variables, this will coincide with any of the asymptotics that you might have seen, for instance, for linear regression or logistic regression. Okay. So how does this help with the actual original problem?
Kabir, you have another 10 minutes.
I'm basically gonna get through this this one step, and that's, I think, somehow that's the meat of the proof. I think it becomes clear what happens after that. Okay, so I think basically the real trick here is that from these auxiliary deterministic quantities, what you see is that these inner products here, like let's say this inner product that appears with gamma D and VSE, this is going to be equal to this quantity, which is some constant. This norm is going to be equal to some constant, it's just C3 squared. Same thing with this norm here, it's just C4 squared. So what we can do is in this A of gamma and gamma D, you see that if I take the gradient of A gamma and gamma D, so if I take the gradient of this thing, let's say in U, what this looks like is I'm going to pick up a negative inner product of gamma D V over root D times U for the norm of U plus D 2 gamma N plus the same panel BV of V minus BU of U. Another important point is once you have these constants, whatever they are, you can make the ansatz that this thing might concentrate around the constant that you see in the fixed point. This norm might also concentrate around what you see in the fixed point. Same thing with this norm of V. This might also concentrate. So what you do is you look at this fixed point and you say, okay, I want this to be equal to 0. Let me come up with a different equation, where in the different equation, I'm just going to plug in what is gamma dV. So I have some constant there. Let's call it, I wrote it down somewhere. So I have some constant here, which is just C1. This motivates So the ansatz is that, what I'm going to do is I'm going to plug in these blue guys by exactly what their deterministic predictions should be according to that quantity there. And I'm going to construct a new stationary point here. Now, what is the nice thing about this stationary point versus this one? This stationary point involves both V and U, and it involves this norm of U. This stationary point has no involvement of V. This only depends on this UAPX. And I'm calling this UAPX because this is exactly this is going to be our approximate stationary point. Indeed, this quantity here, this is the KKT condition of a proximal operator of phi. Okay, so we can rewrite this thing as U APX is the argmin of 1/2C1 U minus lambda C4 gamma n plus DU. Okay? And so this is evidently going to be fine because this is strongly convex and this is just an L2. So these two quantities are exactly the same. This is just for stationary. Now, the claim, which I'll just say, the claim is that that stationary point that we just constructed, where we just plugged in from this deterministic guy, that stationary point is going to make is going to be an approximate stationary point for this auxiliary update. So what the claim is that, let me go here. With the probability at least 1 minus delta, the gradient in U of L U APX, we define V APX in the same way. This is small.
This is gradient of L, not L star, right? L
The
is,
gradient of L.
L is what is inside this A, right?
Yeah,
Okay.
this is. So this is truly the random.
Okay.
Yeah. And the same thing holds for the gradient in V. It's also basically, so essentially this UAPX and VAPX is a stationary point of this. Now, we still, maybe, how much?
5 minutes.
5 minutes? Okay, great. I can finish the sketch in 5 minutes. So once I have these stationary points, again, what I said is that I only have information about minima, just the value of this problem. How do I actually convert this to information about the saddle point? Well, if I look at these saddle points, so if I look at this thing, for any fixed U, this is a strongly convex function in V. And for any fixed V, this is a strongly concave function in U. So what I'm going to do is I'm going to look at these functions just at UAPX, VAPX, and I'm going to look at perturbations around the minimum. So for a strongly convex function, so it looks like this. If this is my minimizer, and let's say I go delta n away from the minimizer, then I know that up here, I'm going delta n squared. So roughly speaking, what this means is that if I can control the deviations of the loss on the order delta n squared, then I can get something on the parameters on the order of delta n. Okay. So in particular, you can just write it. We're interested in the event, so we want to show, let's say that the norm of this U value minus this thing. And we want to show that this is small. How can we do this? We can define two events. So the two events are the following. I have omega 1. The event that the min over V, max over U of this original problem, LUV, this is less than the value of L star plus delta. And omega 2 is the event that the minimum over V such that this is not true. So I want to show, let's say that this is less than or equal to delta. The minimum over V such that V minus this quantity is greater than delta n max over U of L U V. This is greater than the same thing, OPT, plus delta n squared. So omega 2 is the event that my minimizer is somewhere above here. And omega 1 is that the value of my problem is inside this. So what this means is that actually this event, V1 minus expectation of this quantity less than or equal to delta n, this is implied by the intersection of these two events. So in order to understand this probability, I just have to understand the probability of these two events. But the probability of these two events are just based on the losses. So in particular, just applying this claim, this shows me that actually I can take delta n on the order log 1 over delta over n to the 1/4. So I lose a 1/2 factor because of the strong convexity. Okay, so I won't take too much more time. This is basically what I wanted to get through. The generalization to the case where you have memory and you use correlations follows this exact same strategy. So you take your saddle update. Now, how do you pass to the auxiliary update? You take this and you do what you would expect to do. This is a Gaussian random matrix, so you orthogonalize it with respect to the past. Now, the issue is when you orthogonalize it with respect to the past, you get a matrix which you're projecting onto the span of your V1 through Vk and onto the span of U1 through Uk. And this matrix can be really quite nasty. There's no reason you should be able to control it. But the same idea that we had here, where when we looked at this KKT condition, we had these quantities like the norm of U, the inner product of gamma D and V, that by some ansatz we know concentrate to some value. In those projections, all of the terms in those projections, those concentrate around some fixed values. So what you can do is you can come up with another surrogate approximate stationary point using this. So plug in what you know these are going to be, and then just study that. So that's basically, once you have this plan in your head, it's fairly streamlined to go through and do it like that. So yeah, basically the upshot is that this technique is what you can use to analyze these types of algorithms. There's a bunch of open problems here, which maybe I won't have time to talk about, but I'm happy to chat afterwards.
Any question?
These are iteration 1, right?
This is for iteration 1, yeah. So
Algorithm convergence rate.
great question. Okay, so this is actually one of the open questions that I wanted to say. So in the case where these are stochastic updates or full batch updates, we basically know how to compute the convergence rates because the state evolution quantities that pop out, they're analytically tractable. So for instance, I can give you some non-standard ones, like take for instance this phase retrieval problem. In phase retrieval, if I apply alternating minimization, we can show that from a random initialization, even though this problem is non-smooth and non-convex, you're going to converge to a local converging region in log d many iterations. And then in that local basin of convergence, you converge superlinearly, but the convergence rate is with exponent 3/2.
Even with first order methods?
This is with alternating minimization. With the first order method, you also converge, you don't converge superlinearly in that basin. With the first order method, so for subgradient descent, you converge linearly, but you can compute the exact constant that you converge linearly with. So you know the sharp constant. This is for large batch methods. For these which are full batch methods, so large batch methods means I never reuse the data. So I basically can do what I just did here and repeat that at every step without orthogonalizing. The issue is that when I try and orthogonalize at each step, I'm going to get a deterministic formula, but in general, that formula is not the most tractable in the world. So one of the questions which I'd like to understand is like that sharp 3/2 rate of convergence that you get for alternating minimization, can you get that in this regime here? Simulations seem to indicate that that is the case, but analytically, we haven't been able to show it.
have a question about this random variable value function, the minimization problem. How do you connect that to this auxiliary minimization problem? So it has to a limit. How do you go from a vector value to this?
No, there's no limit that you're taking. It's just the construction. So they have, a priori, they have no reason to be the same in any way. They're somehow like, yeah, they're not really like taking the limits. It's basically like viewing this A just as a deterministic function. So you're not really taking the expectation of it, but it's just replacing every quantity here with their L2 variance. So you're just looking at the random variables.
Why there's this Hilbert space involved?
I don't have a good a priori reason. It basically like the reason why you need to lift to it, or you don't need to, but the reason why we lift to it is because it makes these proofs of uniqueness and existence very straightforward. Because this is going back to the question you asked earlier, which is like, this has a lot of nice structure. It's convex and concave. This is not. But when you pass to the Hilbert's problem, you get to inherit this like convex concave structure, and you can use that to prove something variational. So you can use that to prove existence and uniqueness, and then you can use whatever you get to plug into this.
It seems that you make even concave and convex, and by changing sort of geometry, by lifting to the Hilbert, I don't know how you come up with the geometry, but it seems that you make the function more.
Yeah,
curvature.
exactly. It is kind of like that. Like you lose all of these like little. It's not quite like passing to a population limit, but in spirit, you're doing kind of the same thing, where you get a bunch of little fluctuations in these random problems, and you smooth out those fluctuations when you pass to that problem.
Any question?
I also wanted to ask, at the beginning, you mentioned the sort of like statistical and computational, and sort of where maybe
Yeah.
it's related to that question.
Yeah, okay, great.
What is it?
So this is also related to the convergence rate question. So basically, in both of these, in the case where we have stochastic updates or we have large batch updates, we know how to do this because precisely these deterministic quantities are tractable. So one example I gave here is for a convergence rate, you have alternating minimization. It's going to converge at rate superlinearly with exponent 3/2. On the statistical side, we also know that it its iterates converge to some point. So there's theta star, and there's this noisy ball around theta star. We know statistically that the radius of this noisy ball is of order sigma root d over. So there's a minimax lower bound that says that you can't have any method. So information theoretically, you can't do any better than this term. What we can show using exactly these deterministic predictions is that in these large batch methods, you converge somewhere in this ball. You converge superlinearly to a point in this ball. And all of your iterates then stay in this ball after that. So statistically, you achieve the minimax rate.
Is that a little bit vacuous? Because isn't the large batch sort of setting kind of saying you have enough data already?
No, not necessarily, right? Because in the large batch setting, you can still take this. This is information theoretically, you need this. So you're only inflating it by a lot, in fact.
Maybe I can say so I'm kind of more interested in some of the high dimensional statistics stuff. So I'm curious, like in settings where maybe n is not larger than d, is there anything we can say?
You want like d over n converting to a constant, like this one?
Sure, something like that, yeah.
You can still, yeah, so what you can, I don't know downstream what the consequences you can say in this thing. These predictions are correct. How to analyze them and extract this prediction. And if you can say something that I
So
don't.
you get an asymptotic error that's constant order, not the vanishing order.
Yeah, you get the constant order.
You can also do deterministic equivalence with different tools
Yeah.
in this proportional regime.
No, but in this proportional regime, you won't be able to, I don't know what other tools you'll be able to use here, because for this phase retrieval problem, for instance, because you have non-smooth loss and your updates are also non-smooth. So
The Elliott packet, Courtney packet, they have something.
depends on what method you use. But there mostly it's for smooth losses and specifically for SGD and for online method. So here, if you're doing a full batch method and you have non-smooth losses, these won't work. And if you're doing a higher order minimum.
Okay, let's send speaker again.